Okay, so the next paper will be LiDAR vision fusion inspection of perforated diaphragm zones in multi-Girder bridges. It's a hard title I've ever seen. Anyway, Weiwei is going to present this.
Thank you. Good afternoon, everyone. I'm Dr. Weiwei Chen from University College London. Now, I'm an associate professor at Bartlett School of Sustainable Construction Department, especially focused on digital twin, 3D reconstruction, digital construction part. Today, I would like to present one of the research work from our group. Yeah, the title is very complicated. It's LiDAR vision fusion inspection of the perforated deformed zones in multi-girder bridge using an Elios 3 confined space drone. Okay, let's see the problem statement. As we know that there are the inspection challenges about the bridge, especially the corner under the bridge, that's a deck part. So from the multi-girder bridge, the underdeck from is usually deep, it's narrow, and also it's very dark. So the environment is not perfect for us to detect. So based on this based on the difficulty for human being to inspect, so we want to see, is there any better solution we can provide to do this, to address this problem. So first, the GNSS signal are blocked by the bridge deck. And also secondly, the illumination is very limited because it's very dark. And thirdly, the available headrooms, the line of the light is highly constricted. And so in many cases, the inspector, we need the scaffolding, so the lifting equipment and the rope access, but it's very risk. And another challenging is about the data quality. So the manual inspection often depends on the haven of the inspector experience, and also the quantitative and the traceable documentation is also limited. So the key research gap is the most existing UAV we can use, right? The workflow focuses on the external bridge surface, but the robust inspection is not very good especially for the underdeck cavities. So that's why we focus on this problem. As I mentioned this one, so we have three objectives. The first one, we propose one topological gateway planning method. In our inspection scenario, okay, we want to use the diaphragm opening because this one not treated as the obstacles, and instead they are modeled as the transport gateway between the joint gird base. And secondly, we developed a LiDAR vision fusion pipeline. So this pipeline based on the LiDAR SLAM, so we provide the geometric reconstruction and the coverage verification, and also the close-range RGB images can support the defect documentation and qualification. Thirdly, we designed the Bay-indexed digital inspection protocol. So this protocol allows us to do the each inspect, to do the each defects to be linked with the surface bay. And based on that, we can make the inspection results more useful for the maintenance decision. So overall, that's our solution. So based on that, we also want to see, because there are lots of the UAV bridge inspection people have done, right? And we try to see, is there any more new device we can use? And the earlier study mainly focused on the near surface. We fly the UAV, the drone to capture the images, and also it's a visual-based control. More recent work have paid more attention about the image quality, the safety issue, and the operational feasibility. Okay. However, the most UAV, the drones, the inspection workflow are still designed for the external and the line-to-science bridge surface. So the underdeck, so the underdeck part is more challenging because they are the GNSS defined, so it's poorly illuminated and also close to the structure surface. Okay, so based on this problem, some emerging solution comes, but all this based on the beam-informed planning, the collision-tolerant drones, or the LiDAR SLAM. But all this integration technology is still limited. So based on that, we want to explore more. So that's the motivation of our work. Okay. Another related work is a 3D reconstruction and the vision detection. So we can see from the table. Okay, we combine the different solution, like the SFM, the portal, the visual SLAM, the LiDAR SLAM, and also we compare the difference between this solution. Okay. And after we compare this, you can see the LiDAR SLAM and the RGB imaging. So we can provide the 3D spatial context, and also this vision provides the detailed defect information. So that's our integrated pipeline. Okay. Based on that, we search one device we can use. This one is commercialized. It's the Elios 3 platform. And this one, it can provide the advantage for us to do the inspection. The first important component is the collision tolerance cage. Okay, it can protect the drones. So even it's very close, very near to the surface of the bridge. And the second component is onboard LED lighting. Okay, so this one can be very useful for the dark environment. So we can still get the high resolution image based on that. And thirdly, the LiDAR sensor, which supports the real-time SLAM mapping and also the localization without GNSS. So even there are some things we can still get data. So finally, based on this, so the RGB camera can also provide the very close range vision evidence for the defects documentation. So in our workflow, you can see the system can operate offline, and it's very important for the restrict or the network illimited environments. And also based on that, we have 3 steps. That's our mission design. In the step 1, the regional interest, the ROI is decomposed into the girder base and the diaphragm station. So each bay is assigned to coordinate the local frame. It's useful for the later reporting. And in step 2, so the diaphragm opening are modeled as a node in one gateway graph. So the girder base and the opening are connected by the traversable edges. Okay. In step 3, the drones flow are depth first the traversal strategy. So we can visit all the bay systematically during the flight. Okay. The drone can perform the slow curve imaging as a slow standoff distance about 0.25 meter. Okay. That's the 3 advantages in our solution. And afterwards, we want to see after we get the data, after we aggregate the data, okay, the LiDAR SLAM is used to reconstruct the inspection undertake cavity. The 3D reconstruction is not only for the visualization. More importantly, it allows us to verify the inspection coverage quantitatively. The coverage ratio is calculated based on the surface elements, and also this visible score is above a predefined threshold. The visible score considers the LiDAR lines outside camera reflected information. So in the test field, okay, you can see. So sorry, in the test field, we realized it can achieve the 98.75 coverage over the 12 meters ROI. And also we get the 12.4 million points, about 1 centimeter resolution. I can show that clearly later. And here there's also the next part is about the visual-based detection, documentation, quantification. You can see about the crack detection, we use the transformer-based crack segmentation model. It's the CBR former. We also published one paper before regarding this. You can refer before publications. So after segmentation, the crack length is calculated using the Multi-Girder skeleton. So the crack width is estimated using the distance transformer. And for the leakage and the collision, like the detects, so we adapt the SASBE thresholding and the zone cleaning. So after we can calculate the area and the length metrics. The key advantage about this solution is that each RGB images is associated with an SLAM diverse pose. So the detected defects, so not only visible in the image, but also linked to the 3D coordination. And for this case, you can see we try to test our workflow, our solution, and we selected one bridge in Honghu in China. So we select around 12 meters long and fly this device once. It costs 5 minutes. And finally, you can see we got this, the ROI, the 4 gateway and the 3 diagram opening along 12 meters. And the data is synchronized with LiDAR and RGB recordings. So afterwards, we did the comparison between the solution by manual and the solution from the Elios 3. And you can see from the figure, we reduce the time 80% from 25 minutes to 5 minutes. And the coverage, because by manual, we can only cover 65%, but this solution, we can cover 98.75%. And the minister standoff, we reduced to 0.25 millimeter. And also the safety is, we reduce the risk. So the risk is low in this solution. And also the digital transactability is high. And also we don't need the human enter. So it's based on this device. And for this example, you can see we compare the especially 4 type of crack, 4 type of defects, the crack, leakage, corrosion, and the influence. And also we compare about the coverage. And based on this solution, you can see we can get the different evidence for the different type of defects. Like the crack, we get the RGB, and the geotag leakage, we get RGB 3D images, and the caution RGB 3D. So that's all information we can collect it based on this solution. And finally, you can see until now, we already defined the workflow based on this device. The Confined-Space drone workflow can enable the systematic bay-to-bay conversion through the diaphragm opening, and also we reduce 80% of time and increase the coverage. The coverage is SLAM verified. And all this is a 3D spatial transability is also very useful for the next step. And also this is the first work we formalize the diaphragm opening traversal as the topology planning problem. But you can see there are still some limitation because we only focus on one bridge. So in the future, we want to do more, focus on a different type of bridge to test our solution. And also for the future, for the SLAM comparison, we want to also qualify the LiDAR advantages in the underdeck environment. And also for the benchmarking, we want to explore more. And also the longitude study, we also needed to consider about over 12 months in the future. So that's the overall solution and conclusion about our research. Thank you very much for your attention.
Many thanks for your presentation. It was really interesting. So we're taking question right now. Do we have any question here? Nothing? Yourself. Okay.